Hi folks, welcome to another screencast. So I'm actually going to basically redo what I did during the online session on Thursday. For those of you who joined me on Thursday, you know that it was a little bit clunky because the technology that worked so beautifully at home on Wednesday night did not work on campus on Thursday. So we made it through a class and it was quite a fun class, but the video was really quite terrible. So I thought I would just redo that in the screencast. And so I think you'll find that much more efficient anyways. All right, let's get going. So first of all, I asked you for some feedback in a survey. And in the survey, I learned that you're quite concerned about running into technological issues during a timed CrowdMark assessment in particular. You're really worried about not being able to upload your solutions by the deadline. And so I've certainly made note of that and decided that I'm going to be more generous with the time and also try to be online at the same time so that you can ask questions if needed. So what I'd like to do today is follow up on the first video that I posted in week 10. The first video was about finding critical points for 3 different functions, and I would like to return to those exact same examples, but this time characterize those critical points. So we characterize critical points by using the second derivative test. So for the second derivative test, we really rely on this function d, which is made up of a combination of all of the second partials of the function f. So it's f sub xx minus f sub times f sub y minus the mixed partial derivative squared. So that quantity is really, really important. And the idea is that you evaluate this quantity at each critical point. So we evaluate that at each critical point a, b. And if d is positive, then you're in either case 1 or 2. And then you have to also take a look at what is the second partial with respect to x at AB. If it's less than 0, then you have a local maximum in the first case, or if it's greater than 0, then you have a local minimum, as in that's the second case. If you found out that d at the critical point was less than 0, then you're in case number 3, and then you can conclude that the critical point is a saddle point. And in the few unfortunate situations where d evaluates to be 0, unfortunately the test is inconclusive. You could have either a local max or a local min, or you could have a saddle point. So let's take a look at the first example. I've already filled in a little bit because we've already gone through those details in the first video. So for this particular surface, we found one critical point, namely the point 3 minus 4. And so now we want to use the second derivative test to characterize this critical point. So what we need to do is we need to calculate all of the second partial derivative. So f sub xx is the derivative with respect to x of f sub x. So I've got 2x minus 6. The 2x gives me a 2, and the minus 6 gives me 0. And so f sub xx is equal to 2. And then we need to find f sub y. So that would be the derivative with respect to y of f sub y. We have 2y plus 8. The derivative with respect to y gives me 2. And we also need to find the mixed partial derivative. And so now we could go either way. We could either take the derivative of f sub x with respect to y. Well, that's going to be 0 because f sub x doesn't depend on y. It is 2x minus 6. There's no y's there. So as far as y is concerned, 2x minus 6 is just a constant, and the derivative is equal to 0. Now you could have also taken the derivative with respect to x of f sub y, and then you would still end up with 0. All right, so now that we've got all of the second partial derivatives, we can construct the function d. And so the function d is f sub xx times f sub yy minus the mixed partial squared. And so in this particular case, it is just going to be 2 times 2 minus 0, which is equal to 4. Now 4 is greater than 0, so we have either a local max or a local min, but we, in order to distinguish, we need to also take a look at the sign of f sub xx. So here I'm going to write, so we either have a local max or a local min. And so to distinguish, we can calculate f sub xx at the point 3 minus 4. Notice that when we evaluated d, it didn't matter. For any point, d would be equal to 4, and certainly it would be equal to 4 at the point 3 minus 4. But for f sub xx, we have to, oh no, we don't have to evaluate it either. It's just equal to 2. Never mind. Anyway, it doesn't matter. It's fine to write that at the critical point, f sub xx is equal to 2, which is greater than 0. And because f sub xx is greater than 0, we can conclude from the second derivative test that the critical point 3 minus 4 is a local min. Okay. Now, if you wanted, you could calculate what is the z value. So I'm going to do that on the next page. At the point 3 minus 4, we have z is equal to f at 3 minus 4, which is equal to 3 squared minus 6 times 3 plus minus 4 squared plus 8 times minus 4, which is equal to 9 minus 18 plus 16 minus 32. And when you work that out, it ends up being minus 25. So there is a local min at the triplet xyz is equal to 3 minus 4 minus 25. Okay. And I'm quite flexible about how you report these answers. If I want you to give me the triplet XYZ, I'll be very clear that that's what you would need to do. All right, so we have a local minimum here. Of course, we can use Wolfram alpha to visualize this surface, and it turns out to be a paraboloid. So this here is a paraboloid. And the minimum is at over here. It's the coordinate is at minus 3. No, it was 3. 3 minus 4 minus 25. Okay, and on the contour plot, you can see that there's the minimum is right there, and this is the point 3 minus 4. Oh, yeah, that's really hard to see, but hopefully you can see that. All right, good. So that was the first example. Let's take a look at the second example. Again, if you've watched the first video, then you will have already found the first derivatives for this particular function. And so I've already written them down over here. That saves us a little bit of time. Now, in order to find a critical point, we need to satisfy these two conditions simultaneously. Oh, that didn't fit. That looks terrible. Anyways, simultaneously. So the first equation, I can rewrite that as y equals x squared, and then substitute that into the second equation. So substitute into the second equation gives that x minus y squared. Well, y is x squared. I square that. That has to be equal to 0. So that says that's equivalent, I'm using the double arrow there, to saying that x minus x to the 4th is equal to 0, which is equivalent to, if I factor out an x, I'm left with 1 minus x cubed. And now this, of course, then says that either x is equal to 0 or x cubed is equal to 1, but the latter, x cubed is equal to 1, is the same as saying that x has to be equal to 1. All right, so then case that x is equal to 0, if we substitute x equal to 0 into 1, we get that y is equal to 0 squared, which is equal to 0. Therefore, the critical point is 0, 0. And then when case, the case where x is equal to 1, we substitute x equal to 1 into the first equation, and then we get that y is equal to 1 squared, which is equal to 1. Therefore, the critical point is 1, 1. So we found two critical points, 0, 0, and 1, 1. And then on the next page, I'm going to characterize those critical points. So from the previous page, we had f sub x is equal to 3y minus 3x squared, and f sub y was 3x minus 3y squared. That then allows us to find the second partial derivatives. F sub x is the derivative of f sub x with respect to x. So 3y gives me nothing, minus 3x squared gives me minus 6x. And f sub y, I take the derivative with respect to y of f sub y. The derivative of 3x is 0. The derivative of minus 3y squared is minus 6y. And then the partial derivative that is mixed, f sub xy, is, let's just take the derivative of f sub x with respect to y. So that would be 3. We can just, of course, check. If I had started with f sub y and taken the derivative with respect to x, I also would have ended up with 3. So that's terrific. So now we can put the function d together. We're constructing it and saying, well, that's f sub xx times f sub yy minus f sub xy squared. So that is going to be minus 6x times minus 6y minus 3 squared. So that becomes 36xy minus 9. Notice that this is different than the first example because here d is not just a constant, it depends on x and y. So I really do have to evaluate d at both of the critical points. So we'll do the case where we have xy is equal to 0, 0. What is d at 0, 0? Well, it's 0 minus 9, which is minus 9. Okay, so our d is less than 9, so we're in case number 3 in the second derivative test. So therefore, f of xy has a saddle point at 0, 0. Let's take a look at the other critical point, the case where xy is equal to 1, 1. We can evaluate the function d at 1, 1, and we end up with 36 minus 9, which is equal to 27, which is greater than 0. So in this particular case, we also need to evaluate f sub xx at 1, 1. F sub xx at the point 1, 1 is minus 6 times 1, which is minus 6, which is less than 0. Okay? This together means that f sub xy has a local maximum at the point 1, 1. Okay? Now, I've already plotted these functions. I've plotted, or no, sorry, one function, of course. I've plotted the surface as well as the contour plot. And at the point 0, 0, we had a saddle, and so the point 0, 0 is right about there. And so it's a little bit hard to see on this particular graph, but basically yeah, how am I going to show that? Yeah, in the direction of y, the surface is decreasing, and in the direction of, oh sorry, that was the that was the direction of x. As x increases, the function is going down, and as y no, this is really hard to see. Yeah, you just have to accept that it's a saddle point. There are better surfaces where it's easier to see what the saddle point is. What about the point 1? This is really unsatisfying. My apologies for this. At the point 1, 1, there's a local maximum. That is much easier to see. So there's a local max at the point 0, 0. No, at the point 1, 1. The point 1, 1. And this one here, that was the saddle. So there's a saddle at the point 0, 0. Okay? And if you're looking on the contour plot, this here corresponds to the saddle at 0, 0. And the local max is right over there at 1, 1. So there's a local max at the point 1, 1. Okay. Yeah, it's easier to see on the contour plot that you've got a saddle point because you've got these colors that indicate the heights, and so because of the contour crossing over here at the point 0, 0, that indicates the saddle. All right. The third example, that one was the surface f of xy equals 2x squared minus xy plus y to the fourth. In the first video, I left it to you to find the critical points, and some of you indicated that you wanted me to work through that. So I've already found the partial derivative with respect to x and the partial derivative with respect to y. And remember that we have to have these equal to 0 simultaneously. So the first equation, I can rewrite that as y equals 4x. And then let's substitute that into the second equation. And so doing that gives that 4 times y cubed. Well, y is 4x. We're going to cube that. And then we still have to subtract x. I've turned the terms around. That has to be equal to 0. So that means that 256 x cubed minus x has to be equal to 0. So that means that, well, I can factor out an x, so that's 256x squared minus 1 is equal to 0. So that means x equal to 0, or 256x squared is equal to 1. That is the same as saying that x squared is 256. No, 1 over. And that means that x is equal to plus or minus 1 over 16. Okay. So we have 3 cases here. The case where x is equal to 0. What is the y value then? Well, from the first equation, y equals 4x, so y equals 4 times 0, which is equal to 0. Therefore, 0, 0 is a critical point. Okay. Case x equal to 1/16. What is then the y value? Well, it's 4 times 1/16 from the first equation. and so that is equal to 4 over 16, which is equal to 1/4. Okay? And therefore, the point 1/16 1/4 is also a critical point. And then last but not least, when x is equal to minus 1/16, then what is the corresponding y value? Well, it's 4 times minus 1/16, which is minus 1/4, and therefore minus 1/16 minus 1/4 is the third critical point. Okay, so that's basically redoing what you should have done during the first video. And now let's characterize those. So again, our first derivative with respect to x was 4x minus y from the previous page, and f sub y was minus x plus 4y cubed. Okay, so now we have enough information to find all of the second partial derivatives. So f sub x, that's the derivative of 4x minus y, which is equal to 4. And then f sub y, the derivative of f sub y with respect to y, that's going to be 12y squared. And f sub xy is the mixed partial. If I take the derivative of 4x minus y with respect to y, it is minus 1. And of course I could have taken the derivative of f sub y with respect to x, and same thing. It's minus 1. So now I can construct the function d, which is f sub x times f sub y minus the mixed partial squared. So that is 4 times 12y squared minus 1 squared. So that's 48y squared minus 1. Okay, so now I have to evaluate what d is at each of those critical points. So we'll do the case where the critical point is xy is equal to 0, 0. So at 0, 0, what is d? Well, d is equal to minus 1. And that's less than 0. Therefore, 0, 0 is a saddle point. All right, and let's do the other ones. So let's start with xy being equal to 1/16, 1/4. The d value at 1/16, 1/4 is equal to 48 times 1/4 squared minus 1. So that is 48 over 16 minus 1, which is 3 minus 1, which is equal to 2. That's positive. And that says that, well, we have to do a little bit more work. We also have to find out what f sub xx is. So f sub xx at 1/16, 1/4 is equal to f sub is 4, which is positive. Therefore, this critical point 1/16, 1/4 is a local min. Right? So if you just look up your second derivative test, you'll find that it's a local min. And then the last case, xy is equal to minus 1/16 minus 1/4. The d value is actually it's the same. The fact that it's negative doesn't matter. So it's also equal to 2 f sub xx at 1/16, 1/4. No, at the negative of those is equal to 4, and therefore the point minus 1/16 minus 1/4 also is a local min. Okay. And then on the last page, I have visualized this particular function, and there's a local min over here, and a local min over there. And at the point 0, 0, we have a saddle point. So we have a saddle at the 0.00. This first local min over here, this one here is at 1/16, 1/4. And the other one on the left-hand side, this is a local min at the point -1/16, -1/4. All right? All right, so that concludes this particular video of characterizing critical points. So thank you very much for listening, and we'll see you in lesson number 3. Bye.